Okay, hello and good morning everyone. Thanks for joining today's webcast. My name is Amir Al-Munajed. I'm with AnyBody Technology, and I'm very happy to have Tim Weber from the OTH Regensburg with me today. He will give a presentation, or he will present his study, what he has been working on over the last couple of years. So very briefly for today's outline, so I will start with a couple of slides to show you who and what is AnyBody. Then I will hand over the microphone to Tim, and then he will present his study with the title Biomechanical Outcome of Total Hip Replacements Using a Patient-Specific Musculoskeletal Model. And then at the end we will have a question and answer session. So that brings me to the point that you can type in your question while we are talking. So when Tim is presenting later on, you have a question, please feel free. You have a question box behind the orange arrow of this GoToWebinar window. There's a questions box, and you can type in your question, and either some of the panelists that are here next to me or will answer it immediately, or we will talk about it later on live and try to answer your question. So another point is we will record this webcast, and we will put it within the next couple of days on our homepage and on our YouTube channel. And we will also hand out this presentation, Tim's presentation, as a PDF, and we will hand it out to you afterwards. So if you miss something, it's also you have the chance to either listen again to the webcast later on, or you can look in the PDF later on. So very briefly, who is AnyBody? So there's AnyBody Technology. So this is the company in Aalborg, Denmark. We also have an office in Boston. We develop and the AnyBody modeling system, and we provide licenses, training, and support around this AnyBody modeling system. And we also do consulting with this AnyBody consultant modeling system. There's also an AnyBody research group, which is the main one is based in Aalborg University. There's Professor Rasmussen. He's the founder, and he's still the CTO of the company. He does a lot of research in the area of biomechanics, orthopedics, ergonomics, sport, and automotive. We also have a AnyBody research group in Colorado, School of Mines, by Professor Petrella. And there's another one in Germany, hosted by Professor Dendorfer at the OTH Regensburg. They do a lot of biomechanics, orthopedics, gait, and also sport and automotive. And Tim Weber, the presenter from today, he's from this lab from Professor Dendorfer, and he will present his work later on. So very briefly, what is AnyBody? We use the abbreviation AMS, which means the AnyBody Modeling System, which is the toolbox. So this is the software itself. And inside this software, you can load different models. And therefore, we have the AnyBody Managed Model Repository. Abbreviation here for is AMMR. So this includes all the information to create a body model, a full human body model, with different scaling laws, with different options. You can choose different legs, different feet, different settings for your body model. And it also includes a library of applications. So you have different motions or activities that this body model can do in a different environment. So this all is the AMMR, so this AnyBody Managed Model Repository, and you can of course change those models according to your needs. AnyBody does musculoskeletal simulation. We use the activity, meaning the motion as input. We have a full body model with bones, joints, muscle, and ligaments, and then we compute muscle forces, activities, power, and also joint forces, moments, etc. for this activity with the full body model. This principle is called inverse dynamics. So that means input is always the motion and output is the internal forces. We can also compute forces to an environment, like we can predict ground reaction forces or some interaction forces to some devices. Anybody is usually found in those 5 areas. So if I start on the top, so in product design optimization or also development of products, you can, for example, optimize a wheelchair to have the lowest loads in the shoulder or in the elbow joint. If I go to the right, that's also very close to ergonomics. You can do analysis and also documentation. For example, in the automotive area, you can look at ingress, egress, where are the lowest knee joint forces or where are the lowest spinal loads during certain activities in the human body in an automotive environment. If we go further down, there's also the option of use AnyBody in surgical planning, evaluation, and failure analysis. This is where today's webcast is orientated. And you can also export, if I go to the left here, you can export all loads, all physiological loads for finite element analysis. And then finally, we also have a gait application called AnyGait to process C3D trials, so mocap, motion capture, and analyze it in a musculoskeletal way. This works that you load an activity of daily living, so we have a library for that, or you can create your own activity, and then you analyze the muscle activities, forces, joint forces, moments in AnyBody. So this is the standard workflow. However, you can also have an advanced workflow. For example, you can use patient-specific information. Let's say if you have a CT scan in a certain area of your patient that you want to analyze, you can use that data and create your own patient-specific model. And here I also show you can export all the loads into finite element models. You also have the possibility to add an environment or add devices over SolidWorks, for example. So if there's a translator from SolidWorks to AnyBody to translate an environment designed in CAD, so in SolidWorks to AnyBody. And there's also the option to hook the AnyBody up with certain advanced scripting languages like Python, MATLAB, or some optimization software. But I think I've talked enough for now about AnyBody itself. So today we have Tim Weber with us. He's a diploma engineer from the University of Applied Sciences in Regensburg. He finished in 2010. During his stay, he did a research semester at the Royal College of Surgeons in Ireland, in Dublin. And also in 2009, he did an Erasmus semester here at AnyBody Technology. And since 2010, he's research associate at the Laboratory for Biomechanics, the Faculty of Mechanical Engineering at the OTH Regensburg, where he works on his PhD thesis. And today's title is once again the biomechanical outcome of total hip replacements using a patient-specific musculoskeletal model. And I will hand over the microphone and the screen now to Tim.
Okay, thank you very much, Amir, for the nice introduction and the introduction of the AnyBody modeling system. I'm Tim Weber, and I'll be talking today about the biomechanical outcome after computer-assisted Femur First versus conventional THR, which is total hip replacement. So first, I want to introduce all the partners that are involved in this study. On this side, you can see all the institutions, which are, of course, us, the Laboratory of Biomechanics, and the University Medical Center in Regensburg, and the University Medical Center in Groningen, the Netherlands. And these are all the companies that are involved in the study. For AnyBody, for musculoskeletal computations, we of course use AnyBody. For medical image processing, we use Simpleware. For finite element analysis, we use ANSYS, and the implant system is a debut implant system. And I'm here in the middle. I'm trying to bring everything together. So first, I want to give you an outline of what you can expect from this webcast. First, I want to give you an introduction of the clinical challenge. Then I'll be talking about verification and validation of our models. Then we'll be talking about the study results and discuss those results, and I'll give a very brief outlook on what can be done with such data. So again, if you have any questions, there is this reddish button on your right, on the upper right, and you can type in questions, and the panelists, Amir or myself, will answer them straight away, or we'll do this after the webcast. So if you have any questions, feel free to ask them. Just a quick introduction of the clinical challenge. We have an increasing number of patients that are subjects to osteoarthritis, OA, and OA is in the hip is the leading cause for pain, stiffness, and difficulty in moving, and more scientifically, term for difficulty in moving is a limited range of motion. And alone in Germany we perform, or the surgeons perform, around 300,000 total hip replacements per year. What is total hip replacement? Total hip replacement itself starts with the resection of the femoral head. Then the traditional way is inserting or implanting the cup, and then the last step is implanting the stem and the head as indicated here. So we have the cup and the stem and the head. So depending on what publication you're looking at, up to 25% of these total hip replacements are still failing. And the question is why? So turns out that one of the major clinical challenges of total hip replacement is malpositioning of the implant system, which leads to impingement, and this impingement leads to an increased wear rate and an increased risk for dislocation. And there are two types of impingement. One is bony impingement, where the two bony structures strike together, or prosthetic impingement, where two prosthetic components strike together. And here you can see an example of a dislocation, which is probably pretty painful. So I want to introduce the Femur First technique. What is the Femur First technique? The surgeons start out with resection of the femoral head, and then they do it the other way around than the traditional way. So they first implant the shaft, which means that the shaft can follow the natural way the bone grew during the lifetime, and then they are able to implant the cup with respect to the stem. So this gives you much more freedom to get an optimal cup orientation. Next, I want to introduce computer-assisted surgery. So computer-assisted surgery is guided surgery to position the implant system with respect to the patient anatomy. And here we use a BrainLab imageless motion capture computer-assisted surgery tool. And the hypothesis is that optimal implant positioning may lead to decreased wear and impingement rates, though yet we don't know what's optimal in biomechanical terms. So to find out what is optimal in biomechanical terms, we set up a study protocol. So we had 60 patients, actually we had 28 CAS-FF, so computer-assisted surgery Femur First patient, and 32 conventional patients, and this is a subgroup of the much bigger Femur First study, and the study protocol you can find in this reference, has been published previously to the study. We have 3 points of time for gait analysis, so preoperative, we have one gait analysis 6 months postoperative, and we have a gait analysis 12 months postoperative. We are very lucky to have postoperative CT scans of all patients, and the study was randomized, double-blinded, and of course we had ethics approval of our local ethics committee. Next I want to introduce our study hypothesis. So which outcome variable did we look at, and which is the regarding hypothesis? We looked at hip reaction forces, at hip reaction force magnitudes, and hip reaction force symmetries. And our hypothesis was that the magnitude is closer to a healthy normal in the CAS-FF group. And for symmetry, the hypothesis was that the symmetry is increased in the CAS-FF group. Our next outcome variable is the hip reaction force orientation, and we had two different variables, the distance to rim and at peak loads. And the hypothesis is that the distance to rim is increased in the CASFF group, and the distance to rim at peak loads is increased in the CASFF group. This is the workflow we're using, and down here you can see, on the lower left, you can see an example gait analysis as conducted in our gait lab. What happens is we acquire volunteer patients, and they of course are subject to certain anthropometrics and certain anatomy. And we invite them for gait analysis, for motion capture gait analysis, where we record the marker trajectories and the ground reaction forces. And those two things, the patients and the gait analysis, are the input for our AnyBody musculoskeletal model. The model itself consists of 3 steps. The first step is scaling the model according to anthropometrics and motion capture, and it's also possible to scale the model according to medical image data. And we get as an output the segment length and masses and joint position. So this is then processed to the kinematic analysis, where we have as an input the scaling and the gait analysis, so the motion trajectory, and the kinematic analysis gives you as an output the gait pattern, so to say the joint angles during walking. And this is processed to an inverse dynamics analysis, where we have the kinematic analysis as an input, and as an output AnyBody delivers us the joint forces and muscle forces. And after you've gone through all these steps, you can evaluate the forces. We've done it in such a way as we have been published previously. So evaluate the forces and kinematics, and it's also possible to evaluate stresses and strains. So this is the model we've been using. We've been using the AnyGait model, which has been scaled according to a static trial. And it consists of over 150 individual activated muscles. We use this nonlinear scaling algorithm to adapt the model to the patient-specific anatomy, and we use the cubic muscle activation scheme as indicated here. So I want to give you 2 examples of one patient where you can see the patient walking at T0 preoperative and at T1 at 6 months postoperative. And here you can see the motion capture experiments, and after all the processing is done, you can see the AnyBody model. Same we did for all patients and for all time points. And you can probably see how the muscle activation changes according to motion pattern and ground reaction forces. I want to introduce a couple of concepts that we used to evaluate the study. One is called dynamic time warping. This allows the computation of typical signals. And down here you can see a reference where they actually introduced the computation of typical signals for joint reaction forces. So what we did with dynamic time warping is we first used it as for the computation of typical signals, and we also used it for the measure of shape similarity of 2 different curves, 2 different signals. So what is dynamic time warping? Dynamic time warping actually is comparing 2 signals where you have a reference signal here and a target signal, and then you compute this dynamic time warping matrix according to this formula up here. So what you basically do is you connect these signals, and you connect the most similar values, and a more picture-like translation of dynamic time warping is actually we make up this matrix of 2 signals according to this formula, and then we optimize this white path through this matrix, which is basically where a river would flow, where the water would go if you would look at this as a matrix. And so what we also did is we compared this with mean signals for 2 very similar signals actually. And you can down here you can see the comparison of 2 signals during walking, and the dashed line is the typical signal and the full line is the mean signal. And for 2 very similar signals you can't see any difference between them, between the typical and the mean signal. If you are using strongly varying signals, just like joint reaction forces are actually during walking for different subjects, the picture is a little different. So up here you can see the dynamic time warping matrix for 2 very different signals. And down here you can see the computation of the typical signals. And I highlighted 3 aspects of the difference of the mean and the typical signal. So the typical signals does not produce such sharp cutoffs as you can see here, as indicated by 1. The mean signal actually underrepresents this area here, so the typical signals is around here, but the maximum value of both the typical and the mean signal is pretty much the same. So what you're doing is you're actually looking at the shape of 2 signals and then computing the typical shape of those signals. You can find a reference here, and it's very nice described actually. You can also use this for more than 2 signals, of course, so you can use it for as many signals as you want, and you can basically use it for all kinds of signals that you want to use. The next concept is our definition of force orientation. We use the radiographic coordinate system since it's very widely used. It's according to Murray. And here I'm showing you how our force orientation is defined. So we have the transversal plane and the sagittal plane. You can see the force, the cup inclination, which is basically the angle of the normal of the cup to the transversal plane, and our hip reaction force, or our force orientation, the force inclination, is here, you can see, and it's with respect to the cup. So all our force orientations are always with respect to the cup. And this is for the inclination angle. And on the right-hand side, you can see the definition for the antiversion angle, which follows the same concept. We have the cup antiversion angle, which is the angle between the normal of the cup and the sagittal plane. And our force antiversion with respect to the cup is in this cup coordinate system. And it's called the force orientation, force antiversion. Okay. So again, if you want to ask any questions, you can find the question box up there, and feel free to leave any questions, and we'll be happy to answer them. So next thing I want to do is I want to talk about the verification and validation of our model and our measurement chain. So for this we set up 3 different studies. First question that we asked ourselves is the result obtained dependent on the mocap analyst? So we're using a video-based gait analysis system where you still need some human interaction, and we asked ourselves if the result obtained is actually dependent on who does this human interaction. So the source of variance is the motion capture analyst, and our study that we set up to analyze this is we had 1 healthy subject who performed the gait analysis. We evaluated this gait analysis 10 times with 3 different examiners. So A was an experienced examiner, B was an experienced examiner, and C was a not experienced examiner. And our target parameter is the standard error of the mean of the hip reaction forces, so HRF, SEM. Next question that we asked ourselves is how big is the influence of marker placements on the result obtained? So the source of variance is the motion capture marker placement, and for this we had 1 healthy subject walking 10 times, and 2 analysts, A experienced and B experienced, applied the marker set in an alternating manner. So what we basically did is we applied the marker set and we ripped everything apart. Then another guy applied the marker set and ripped everything apart. We of course did gait experiments in between, and then we analyzed this, and we did this 10 times in total. And our target parameter is the HRF SEM, so standard error of the mean of hip reaction force. And the last question was, is the method robust enough to produce repeatable results? And our source of variance is the measurement chain. And for this we acquired 3 healthy subjects, S1, S2, and S3, and we let them perform 10 gait experiments. And 1 experienced analyst analyzed the gait trials. And our target parameter was again the hip reaction force standard error of the mean. So these are our verification results. First I want to talk about this plot here. So on the x-axis you can see all the different studies that we set up. So analyst A, B, and C, marker placement A, B, and subject 1 to 3. And on the y-axis you can see the standard error of mean and body weight for the hip reaction force. And what you can see is that the marker placement has the biggest influence on the standard error of the mean. We also had one outlier here, so we concluded that we are pretty safe when we say that we can reconstruct the hip reaction forces with 2 times the maximum standard error of the mean, which was 0.5 body weight. So whenever we have a difference of greater than 0.5 body weight, we can say this is a real difference, and this is not just measurement noise or it's just chance or whatever. And on the right-hand side, we can see the validation of our verification models. So basically all these crosses represent one of the verification experiments models, and the point dashed blue line is the mean of a different publication, Stansfield et al., who used a different model to compute the hip reaction forces in healthy subject during walking, and the full blue line is the confidence interval of his results. And you can see that most, or probably pretty much all of the models are in between the same range that Stansfield et al. Also computed, except for one. So we concluded our model is valid for this investigation that we want to do. Next thing is we compared our hip reaction forces to the HIP 98 dataset, which is publicly available at Orthoload and is all very often used for compare musculoskeletal models with measured values. So they measured hip reaction forces by means of instrumented implants. And what you can see here is on the x-axis you can see the stance phase in %, and on the y-axis you can see the hip reaction forces in multiples of body weight. So the blue lines, the full blue lines, the full blue line is the median of the HIP 98 dataset, and the point dashed line in blue is the 5 and 95 percentile of the HIP 98 dataset. And in gray, so the full gray line, is our computed hip reaction forces, the median of those hip reaction forces, and the gray area indicates the 5 and 95 percentile of those hip reaction forces. And we can see good agreement, especially at the first peak. Not on the second peak, though results or hip reaction forces like this have been reported in the literature. And also the HIP 98 dataset consists of 4 patients, so making statistical analysis pretty challenging. So from this we concluded that we're pretty much on the same, in a good range to compute the hip reaction forces. And we computed, just one more thing to add, we compared our hip reaction forces at postoperative 12 month to the HIP 98 dataset hip reaction forces, since they were the best comparable in terms of postoperative time point. So again, if you have any questions, feel free to leave them in the question box, and we'll be happy to answer them. Next, I want to show you the actual study results. First, I want to start with the hip reaction forces. So again, what we did is we computed the typical hip reaction forces for both of our groups. First, I want to introduce the graphs. So on the x-axis, you can see the stance phase in %, and on the y-axis, you can see the hip reaction forces in multiples of body weight. The very left graph, so A, is the hip reaction forces for the CAS-FF group, and B is the hip reaction forces for the conventional group. The full blue line is our hip reaction forces at T0, so preoperative. Our full green line is the hip reaction forces at T1, so postoperative 6 month, and our full red line is the hip reaction forces at T2, so at 12 month postoperative. And from our verification experiments, we were also able to compute the typical hip reaction force for a normative database, and this is in the dashed blue line. And so what you can see in both graphs is you can see an increase of hip reaction force compared from T0, so preoperative, to T1, 6 month postoperative. The increase is bigger on conventional, in the conventional group, and you can see not as much increase in the CASFF group. At T2, so at 12-month postoperative, you can see that the hip reaction forces are closer to normal in the CASFF group. So this is the CASFF group on the left side, and on the right-hand side you can see for the conventional group that the hip reaction forces are not as close to a healthy normal. So here I have put the normalized walking speed. So we asked ourselves the question, is this probably attenuated to a difference in walking speed between the groups? So what we did is we computed the normalized walking speed according to Hof, and we compared it to first literature data, and then we compared the different groups to each other. So here you can see preoperative for the CASFF group and preoperative for the conventional group. You can see at 6 months postoperative for the CASFF group and for the conventional group. And you can see the results at 12 months for the CASFF group and the conventional group. And there are no differences in walking speed. So this difference of hip reaction force is not only walking dynamics. Last but not least, our walking speed, our normalized walking speed, was in the same range as reported for other THR patients. This was reported by Stansfield et al. Actually. Okay. So next thing I want to talk about is the asymmetry of hip reaction forces. What you're looking at here is back plots. So if you want to use, if you want to look into back plots, just look on the web, look it up in the web. A back plot is basically a two-dimensional box plot. So what you're looking at here is the same concept as a box plot. So the area always encloses 50% of the complete data set. And if you have any questions regarding this asymmetry, just feel free to leave them here. All I want to show you right now here is the concepts of asymmetry that we're using. So first we're using the path length. So before in dynamic time warping you've seen this wide path, and the longer this path is, the bigger is the phase shift asymmetry of two signals. And also the matrix, you can sum up the matrix along this path, and the cumulated distance is a measure of magnitude symmetry. So basically you're looking at two different aspects of signal similarity, or signal symmetry as we call it. So here on the upper left you can see the results of operated versus not operated side, and what you can see is that the CASFF group was walking more asymmetrical at T0, so at preoperative time point, but is getting more symmetrical over the time course, as does the conventional group. And on the lower right hand side you can see our operated side versus normative data. It's not enough to just compare operated versus not operated, because the symmetry can be very good if both sides perform equally poor. So you also need to compare these data to your normative data, and it's the same plot as before, it's back plot, and you can see a decrease of asymmetry over the time course. We checked that these differences were all not significant. So you're looking at that patients were walking more symmetrical after the operation, but the difference between the groups was not significant. Next, what we did is we looked into the hip reaction force orientation. I've introduced the concepts before, so we always have the hip reaction force with respect to the cup. And what you're looking at here is the force inclination and the force antiversion at T1, so 6 months postoperative. On the x-axis you can see the cup inclination, and on the y-axis you can see the force inclination with respect to the cup. And one time for the force inclination and one time for the force antiversion. The blue crosses are the results for the CASFF group, and the red crosses are the results for the conventional group. On the very right of these plots you can see box plots of the force orientations. Up here you can see the force inclination, and down here you can see the force antiversion. And we actually found a statistical difference between both groups, between CASFF and the conventional group, where the CASFF group is closer to optimum. So optimum would be when at 90 degrees, where the force attacks at the center of the hemisphere of the cup. And the same for force antiversion, actually. This is all results for postoperative 6 month, and we did the same computations for postoperative 12 month. So plots following the same logic. You can see cup orientation and force orientation with respect to cup for inclination at 12 month postoperative and antiversion at 12 month postoperative. And we also performed a test on both groups, CASFF and CON, and there's no statistical difference anymore between the two groups, actually. So statistical difference vanishes at T2. Okay. So I just want to repeat the most important results that we've just seen in terms of hip reaction forces. So the hip reaction forces in the conventional groups are closer to a healthy normal at 6 month postoperative. But the hip reaction forces of the CASFF groups are closer to a healthy normal at 12 month postoperative. Our asymmetries decrease more in the CASFF group, but this is not significant. And the CASFF group is closer in terms of phase shift, closer to a healthy normal in terms of phase shift asymmetry. And our orientation is at T1, the hip reaction force orientation of the CASFF group is closer to optimal, and this is significant. And at T2, there's no significant differences anymore between the two groups. So what we conclude from this is for our results for 6 month postoperative, where the hip reaction forces of the conventional groups are closer to a healthy normal, but the hip reaction force orientation is closer to optimum in the CASFF group. And this shows a trend for a lower propensity for impingement and dislocation early after surgery for CASFF, actually. So, and at 12 month, we have an increased phase shift asymmetry, but the CASFF group is closer or practically the same as in healthy optimal in terms of hip reaction forces. So this indicates a possible long-term benefit due to restored walking ability for CASFF patients. Just talking about the strengths and limitations here, we have a comprehensive data set of 32 versus 28 patients, which is a lot for this kind of study, but still, speaking of statistical analysis, this is still a very small sample size. So our study was double-blinded, randomized, and prospective. So this is very nice for this kind of study, but still we would need more patients to be really sure of the effects we're seeing. We've been using a validated and detailed model. So we've been using the AnyGait model, actually from the AMMR 1.5, I think. And also our symmetry measures are not only comparing points of times, but it's rather a measure of shape similarity. So it's measure of the complete shape. So limitations is that you're looking at postoperative 6 month results. We don't have any earlier results, unfortunately. This is because the clinical experience showed that patients are more willing to come 6 months after the operation, not very much earlier. Also, we've been able to combine other postoperative clinical evaluations with our gait analysis. So we basically did this so patients would not drop out, and our dropout rate is actually pretty low. So this is very nice. We only have recorded walking as a motion. More critical motions may be used for bigger effects, and I put ethics here because, for instance, knee bends, letting the patients perform a knee bend postoperative is probably not a very good idea if this is a motion known to be prone to dislocation and impingement. So we can't let let the patients do that actually. And as I said before, a greater sample size would increase the statistic validity of the results. So just quick talk about the outlook, what you can do with such data. We have all the CT scans, so what you're able to do is you can use patient-specific boundary conditions for finite element analysis and look into, for instance, where in the implant system, or looking at implant bone contact stresses and stuff like that. And also you can use the data for further analysis. For instance, you can facilitate it to use it for surgical planning and all this type of thing. So thank you very much for attending this webcast. This was basically my life the last 4 years, and I've now finished, or I'm about to finish my PhD. And thank you for listening, and thank you for letting me give this webcast.
Okay, thank you, Tim. Thank you very much. It looks like you and your co-workers made a very impressive study with lots of input and also very good results. It's very interesting that after this computer-assisted surgery, after this CAS, there's a lower risk of impingement and dislocation, and also in the long-term benefit, looks like this group is doing very well. So I will be looking forward to see what your further results will be in terms of the finite element analysis and see where you're going on. It's very interesting. So before we go now to the live questions, if you're interested in knowing more about anybody or have questions for us, there's the chance to go to our homepage, either the company homepage, anybodytech.com, where you see a list of publications. Also, Tim's previous publications are listed in there. We also have a anyscript.org homepage with a wiki and a forum to discuss or explain things in there. And we have a YouTube channel. So once again, this webcast has been recorded, or I'm still recording it, and it will be put on the YouTube channel later on. Please feel free to still ask some questions. We'll have another webcast. It's more automotive related, so AnyBody applications or musculoskeletal applications in the automotive environment. It's going to be end of October, so in 3 weeks from now. And if you are interested in talking to us or meeting us, I will be in 2 weeks at a conference in Munich, Germany about human modeling and simulation in automotive engineering. Some of my colleagues will be in the Materialize or Mimics conference in Leuven in October, or in the Biomechanical Engineering Society also in October in San Antonio, Texas. So a couple more comments on more general things. So previous webcasts, you can find them as well on our YouTube channel, so especially about patient-specific scaling, and also some advanced features also about this AnyGait model that Tim is using in his work. So please feel free to have a look there, and then see or look a little bit around what you can find there. If you still have questions, please feel free to contact us.